So we were discussing networked embedded systems. In the last class, we had discussed how we can combine sensors with the embedded systems, distribute them all around, and link them up using the network. So today, we shall continue on the same discussions and also look at the ways and means to design network-centric embedded systems. So just to recapitulate, sensor networks are networks that are formed when a set of small untethered sensor devices are deployed in an ad hoc fashion and they cooperate on sensing a physical phenomena. Okay? That physical phenomena may be a natural phenomena, may be a man-made phenomena. And obviously a sensor network characteristics are sensor, observer, and the phenomena which is being monitored. Sensor is a device that implements a physical sensing of environmental phenomena and reporting of measurements. So in this case, we are generalizing the basic definition of a sensor. I hope you realize by now, because a sensor would be actually the actual sensing elements interfaced with an embedded system, which has also got the communication element built into it. We had already seen examples of Barclay mode and Intel node. And in the Intel node, you have seen that the Bluetooth communication protocol has formed an integral part. But it's not necessary that always this kind of ad hoc networking protocols will be there as part of the mode. They can be an additional module plugged in to the sensor node. Observer is the end user who is interested in obtaining information disseminated by the sensor network about the phenomena. Observer may indicate interests or queries to the network and receive responses to these queries. And these queries can be remotely submitted. If you remember the problem of tracking an object, there may be multiple objects entering the system or entering the area being monitored, but the query can be generated at a remote node. Okay, and the basic problem therefore boils down to that of communicating this information back to the query node. So observer becomes a very important component in the sensor network because your data communication requirement is built around the observer's requirement and the application that observer is intending to run on the sensor network. The physical phenomena is the entity of interest to the observer that is being sensed and optionally analyzed or filtered by the sensor network, because this analysis and filtering task can be node centric and need not be centralized. So with this background, what is the basic difference therefore from sensor networks and ad hoc networks? We have seen a simple example of using an ad hoc protocol like a Bluetooth protocol being used with the sensor networks. We can use Bluetooth protocol, even we can use 802.11b in an ad hoc mode with the sensor networks. But by nature, sensor networks are different from classical ad hoc networks. The differences are the following. First is the number of nodes in sensor network can be several orders of magnitude higher than the nodes in an ad hoc network. Okay? And sensor nodes are typically densely deployed. An ad hoc network can be formed because of a set of mobile users moving into a neighborhood at a particular occasion. But in case of sensor networks, the sensor nodes are expected to be densely deployed all around. The sensor nodes are prone to failures, so there should be mechanisms such that these failures can be notified or taken care of. Topology of a sensor network, does it change very frequently? It can change depending on how the network is being set up. It can change if the nodes themselves have mobility. That means nodes if they can move around. If we consider a set of swarm of robots, okay, that is a set of robots communicating with each other and moving around, then obviously the topology is dynamically changing. Sensor nodes mainly use broadcast. This is a very basic difference. Okay, sensor nodes mainly use broadcast. Most ad hoc networks are based on point to point. Okay, most ad hoc networks are based on point to point communication, while the sensor nodes mainly use broadcast. So two sensor nodes can communicate with each other when they are within a desirable range. Because if a node is broadcasting, if the other node is within a particular range, then only it can listen to the broadcast. Sensor nodes are typically limited in power, computational capacities and memory, okay, because they are small elements and they are typically battery powered, because if they are to be deployed in the environment, they cannot be provided with electrical wired power. So, for them the energy constraint is much more stricter than that of your PDA or a laptop, using which you typically build up an ad hoc network. Sensor nodes may not also have a global ID. Just like say a computer, if it is connected on the internet, connected through IP, will typically have an IP address. Now, a sensor node may not have an IP address. So, it may not have a global ID. So, these are the basic differences of sensor networks from that of a typical ad hoc network. And that is why the sensor network problem is different and requires development of different kind of algorithms than that of the classical ad hoc networking schemes. Although it is not that ad hoc networking protocols are not being used in the context of sensor networks. A very important problem in the context of sensor networks is what is called time and space problems, because you have to have a timing synchronization if an event is detected at a node, and if that node has to ask the next node to observe or track the phenomena, then there has to be a timing synchronization, because the next node cannot start tracking the phenomena after an undue delay when the phenomena has disappeared itself. If you remember the problem of tracking, so node A has detected a target. When the target moves away from the observation sphere of node A, node B should take up. Which node will really take up, that is being predicted by node A, and if that prediction is correct, the node B should now start observing the phenomena, and node B should start observing the phenomena satisfying a timing constraint. Okay. So, the time synchronization becomes important issue. Obviously, the other problem is that of node localization. If a node A has detected a target moving out of its sphere of influence, it should realize in which direction it is moving out. Okay. So, it would localize the direction in which the target is moving out, and along with it, it should localize itself in the sensor net in the context of its neighbors, because it has to identify an appropriate neighbor and inform the neighbor to track the phenomena. If it cannot identify the neighbor, if there is an uncertainty in determination of its localization parameters, that uncertainty should be taken care of or should be minimized by instructing maybe more than one node to track the phenomena. Okay. So, these aspects become critically important for a sensor network. Associated with this is sensor coverage, because if I have an area which is to be covered, then I need to know that what is really my coverage area, because then only I can sense that whether my task is over or not, and what can I do as long as the phenomena is within my area of coverage, sensing coverage. Okay. So, all these issues, these are not relevant in the context of a pure ad hoc network, because in a pure ad hoc network your problem is that of simple setting up a communication link in an ad hoc fashion. Here, along with the communication, the fundamental problem is that of sensing and processing of the sensed data. Okay. So, these makes the sensor network protocols different. So, let us look at this example. If I am considering or bothering about the problem of tracking animals. Okay. So, actually if you look into it, this animal or the target is a mobile target. It is moving around and there are these many sensors which are trying to pick up this information. Now, as the tiger is moving, or this is not a tiger, this as the lion is moving around. So, the whole question comes up is that of what is the trajectory which is being followed. So, if you see here, it is T0, T1, T2, T3, fine. So, then there has to be a time synchronization between the nodes to really track the trajectory of the target. Okay. So, what we need a localization, tracking and distributed DSP. Why distributed DSP? Because I need to do a signal processing to identify this is really the target that I would like to observe. Okay. And this is related to data aggregation, okay, because the track can emerge if and only if I can aggregate the data over distributed sensors. That is why data aggregation becomes an important problem. And I can use caching in a very interesting way. So, if I know that this is the target that I have tracked, the target may have certain characteristics. Okay. So, that characteristics if I can pass on to the next node, then detection of that target can become easier. The time delay for the target detection reduces. So, that effectively becomes a problem of caching the target characteristics from node to node for the purpose of tracking. Okay. So, this obviously the whole thing can work provided we can have time synchronization as well as node localization. So, what is the network dynamics? Therefore, this network is basically has got its own dynamics, which is different from any other communication network dynamics. Very simply stated, a sensor network forms a path between the phenomena and the observer. Okay. Why? Because observer in this case, if you find out observer is located somewhere and observer is interested to know the track of the target. So, sensor network is basically providing the path. The observer may fire query at a particular node. In that case, actually the path gets determined, that is I may track the target using nodes A, B, C, and the query may be fired at node G. So, the data aggregated should be transmitted to node G. So, therefore, the goal of sensor network protocol is to create and maintain this path or multiple paths under dynamic conditions while meeting the application requirements. And these requirements, obviously these are generic requirements: low energy, low latency, high accuracy and fault tolerance, because there may be failures and I would need to get the track despite the failure of one or two nodes. So, on the basis of these requirements or these objective, we can distinguish sensor networks into two classes: static sensor networks and mobile sensor networks. In static sensor networks, there is no motion among communicating sensors, the observer and the phenomena. Okay. So, everything is static, and a selected node relays a summary of the local observations to the user. So, it can be a group of sensors spread for distributed temperature sensing. So, if I am interested in monitoring microclimatic conditions, so I can put temperature sensors distributed over an agricultural field, okay, and then I can have the data relayed to the observer. Okay. Now, in this case there can be local processing at the node also. So, if I say that a node is selected that relays a summary of the local observations to the observer, then what is happening? The selected node is actually processing or computing the summary by accumulating the data from the local nodes. Okay. So, I am not communicating therefore, the temperature data from each and every node to the observer, because the communication cost typically would be more than that of computation cost. Okay. So, if we talk about that designing an algorithm for extending lifetime of the sensor network, because the battery is a determining factor for this lifetime, then I would like to have this aggregation or processing done at the local nodes themselves, and then the summary to be transmitted. So, the number of packets therefore being transmitted to the observer reduces substantially and leads to energy conservation. So, these kind of algorithms can be used with reference to static sensor networks. On the other hand, we can have mobile sensor networks or dynamic sensor networks. So, in dynamic sensor networks, either the sensors themselves, the observer or the phenomena are mobile. So, there can be any one of these three, because what I said, a sensor network is characterized by sensor, observer as well as a phenomenon. So, any one of them, in fact there may be multiple of them, can turn out to be mobile. So, whenever any of the sensors associated with the current path from the observer to the phenomena moves, the path may fail. So, what does that imply? That implies that path has to be recomputed. So, I need to have a protocol which is adaptive to the topology of the network. Then either the observer or the concerned sensor must take therefore initiative to rebuild a new path. So, these becomes the basic adaptation of the overall system with respect to the changing topology. Okay. So, either the observer or the concerned sensor must take the initiative to rebuild the path. So, that means if a sensor has moved, it should try to identify or that the sensors in its neighborhood. If it is a broadcasting message, then the sensor in the, whether there is other sensor in the neighborhood receiving the message or not, has to be ascertained and the path has to be accordingly built. So, building paths is the basic scheme in this case. During initial setup, the observer can build multiple paths between itself and the phenomena, and it can cache them, that is, it can make them enabled, choosing the one that is the most beneficial at that time as a current path. So, what does this mean? It means that you can set up multiple paths for communication of information. Okay. And at a particular time, so since you have set up the multiple paths, the multiple path definitions are basically available with you. So, in a sense they have been cached. So, you are not creating the path on the fly. Okay. So, the basic idea is you have created the path, you have during the setup itself, and then what you are doing? You are choosing the one that is most beneficial at a particular time. So, if you find that this path is not working out, you will switch to another path which has been already computed at the setup time itself. Okay. So, if the path fails, another of the cached paths can be used. If all the cached paths are invalid, then the observer must build new paths. Obviously, you can realize the moment you build new paths, there is a delay involved, and that may have an adverse effect on your time synchronization if you are actually observing a moving phenomena. So, what are the different kinds of motion you have? Motion of the individual components. So, first is a mobile observer. A plane might fly over periodically, over a field periodically to collect information from a sensor network. The observer is moving relative to the sensors and phenomena on the ground. Okay. Then you have got mobile sensors. Let us say this is an example, a traffic monitoring system implemented by attaching sensors to cars. So, cars themselves are moving around. Okay. Cars can communicate with each other because they have got the sensors, sensor nodes, about their own observations of the traffic conditions. So, on the basis of that, you have to do the aggregation. So, you can realize that here the aggregation problem would be different from the case where you had a static sensor and the target moving around, that is the phenomena moving around. So, if you have a sensors deployed for animal detection, the basic target tracking problem, where the sensor is static, okay, and you had the target moving around. Okay. So, the aggregation problem between that of mobile phenomena and that of mobile sensors would be therefore different. Okay. Even that will be different when you have got a mobile observer. So, accordingly your protocols for the network communication have to be adapted. So, when we have a mobile sensors, the overhead of maintaining a globally unique sensor ID in a hierarchical fashion like an IP address is expensive and not needed, because your sensor is moving around. Okay. So, IP address is a hierarchical and uniquely associated with a node. So, this whole addressing scheme that we are familiar with in the classical network is no longer valid in this kind of a scenario. Sensors should communicate only with their neighbors that are found. Okay. And repairing a path is used so that the information about the phenomena is always available to observer regardless of the mobility of individual sensors. So, if the sensor is moving around and it finds a neighbor, so through a set of neighbors a path has to be rebuilt for getting the data back to the observer. Fine. So, what we say is that the moment a mobile node moves around, the currently existing path no longer remain valid. Okay. So, the path needs to be repaired. Since the path needs to be repaired, so what does that mean? It means that you identify another set of nodes through which the message is to be relayed. When it is a mobile phenomena, typically the communication should be event driven. That means you are tracking a, say a LAN, tracking a target. So, whenever a node detects a target, that is an event. So, the whole communication therefore should be set up in an event driven fashion. And depending on the density of the phenomena, it will be inefficient if all the sensor nodes are active all the time. Because just consider in a forest, you have put in these sensors all around. It is not necessary for all the sensors to be actively monitoring. It is necessary only for those sensors which have just got the triggering event, and that triggering event may trigger other sensors in a synchronized fashion. Okay. So, only the sensors in vicinity of the mobile phenomena needs to be active. So, therefore, you can realize that design of such sensors also becomes an issue, because typically an external event has to trigger that sensor. So, normally what will happen? Such nodes will be slipping. When the target is in the vicinity, that is a sensor senses the target, that will generate, here sensor I am referring to as a sensing element gets the target, then what it will do? It will generate an interrupt to activate the system which can now start processing the data. Is this clear? Otherwise, there is an unnecessary wastage of resource. The number of sensors in the vicinity of the phenomena can be determined by application specific goals such as accuracy, latency and energy efficiency, because on the basis of which you have to design the deployment pattern, because this deployment pattern is something very, very important. Why? Because if it is a phenomena, what you are trying to do? By putting these sensors, you are doing a space time sampling of the phenomena. Okay? And if you are doing an undersampling of the space time phenomena, you are not making correct observations. Is this clear? So, that matching of your sensor deployment strategy, that is the sampling interval, space time sampling interval, should be such that it matches that of the phenomena. Okay? Otherwise, you will miss out the basic features of the phenomena itself. So, now with this basic background, we shall not go into details of this variety of these protocols, but we shall look at some of the issues and some of the basics of some of the protocols and the designs which are relevant to sensor networks. But obviously, we do not have time to get into their details. So, what is the key issue in medium access control in sensor networks? That is the MAC protocol. The key should be collision avoidance and energy efficiency as well as scalability in terms of node density. Okay. So, energy efficiency significantly affects the network lifetime. Okay. So, if you look into it, obviously what we are talking about, I would like to avoid the collision. The two nodes in the vicinity should not start broadcasting at the same point in time. We should like to have energy efficiency because that significantly affects the network lifetime, and the system should be scalable. That means, if I increase the node density, the network traffic should not be such that actually the channel gets choked, the communication channel gets choked, and effectively I am not being able to transfer the data. So, such a scenario should not happen. So, let us look at one aspect of it, that of energy efficiency. Now, what we have found that common to all wireless network, the major sources of energy wastage is idle listening, because you have got long idle time when no sensing even happens. This is typical to that of a sensor network, but you actually do an idle listening to find out whether there is a collision or not. If you are using a typical collision avoidance protocol, what do? You actually sense that whether there is any communication is taking place or not. If it is not taking place, then you wait for an interval and then you start communicating. That is exactly what is done in 802.11. So, in this case, the listening part is actually the most energy consuming part, because you are listening to the channel. So, the long ideal time when there is no sensing event happens, if the node continues to sense the channel, it will be wasting energy. So, what we need to have a strategy to reduce energy consumption from all above sources. So, therefore, is idle time to listening and collision avoidance, control overhead, and also overhearing. That means, the message which is not intended for you, you should not hear as well. So, how to design such a protocol? Okay. So, we shall look at a very primitive protocol, okay, and basic aspects of that protocol. So, this is called sensor MAC or SMAC. So, the key issue here is periodic listen and slip, and using that periodic listen and slip, you can do collision avoidance, overhearing avoidance, as well as message passing. In fact, the major parts are these: the periodic listen and slip, collision avoidance, overhearing avoidance, and message passing. We shall look at this phenomenon of periodic listen and slip, which distinguishes this MAC protocol from that of your 802.11 protocol, which is for wireless LAN. So, here if you see that what we are looking at, that we are trying to have a phase or a period when the node listens, a period when the node slips, then it listens, then it slips. Okay. So, it is not that it is always listening, it is listening and slip. Now, what is the difference if you see with the Bluetooth? Bluetooth was, there were definite slots available, okay, at which your slaves were communicating with the master. So, there is a basic concept of master and slave, but here we are not talking about a concept of master and slave. In a way, it is an absolutely symmetric configuration with each node configured as such that there is no distinction between master and slave. So, each node follows a periodic schedule. It has a fixed period for listening and fixed period for sleeping. This is the basic SMAC protocol. So, turn off radio when sleeping, so saves energy, and it reduces duty cycle to about of the order of 10%. Okay. So, about 20 millisecond on and 2 seconds off. So, it is a big saving. Although it implies that there is an increased latency for reduced energy. Latency is increased due to periodic slip. So, therefore, how the whole communication takes place? So, you are listening. So, after listening, you can do a broadcast. If I am having basically the neighboring nodes, these neighboring nodes can have different schedules. The nodes can have different schedules. So, when you are broadcasting at this point, the node, this node 2 is in a listen mode. So, it can listen and receive the data. And since they are in different modes, obviously this neighboring node will not broadcast at that point because it is listening. Okay. So, naturally your collision gets avoided. Now, so if we say that preferably if neighboring nodes have same schedule, then also the same issue comes up. So, you have got easy broadcast and low control overhead. So, if they have the same schedule, that is both of them are listening at the same point. So, you know they are listening and accordingly you can act. Now, there can be different schedules followed by a network for different set of nodes. So, if you look into this, I am considering this node as a border node. So, a border nodes can follow 2 schedules to broadcast packets twice, because when if you look into it, there was one point of time here I am broadcasting packets for this network. When these packets are getting broadcasted, these nodes are following a slip schedule. So, since they are slipping, this packet cannot be received. So, I have to have another broadcast. So, the neighboring nodes following different schedule actually increases in a way control overhead, because you have to do a multiple broadcast. So, what we say, it is a preferable if neighboring nodes have similar schedule. Okay. But if I know exactly, so the other issue is what I illustrated here, that if I have these kind of periods defined, then these gets also naturally lead to avoidance of collisions. No 2 nodes will be really trying to broadcast at the same point in time. Is this clear? So, this is the basic philosophy of the SMAC or sensor MAC protocol. Now, obviously, you can realize since it is a periodic listen and slip at each node, there is a substantial saving in the energy, and the nodes are not really listening to the channel to avoid or detect collision, and that is the major source of energy consumption. There is a ZigBee protocol which is actually different from this, which is currently emerging IEEE standard for this kind of sensor networks, and ZigBee refers to an industry consortium which ensures interoperability by defining higher layers and application interfaces, and it is optimized for low data throughput with simple or no QoS supports, and achieves power efficiency from physical and MAC layer. In a sensor MAC, I have talked about the power efficiency primarily from MAC layer point of view, but from the physical layer point of view also, how you specify your communication pattern, that is your usage of physical layer, that can also lead to energy saving. Next, let us look at an adaptive topology. Okay. So, adaptive topology basically provides a mechanism to adapt the existing topology with respect to the application needs. I have already illustrated that concept, that when the nodes are moving around and I need to establish a path. So, this kind of adaptation is essential. So, what we say is that we have got a self configuring system that adapts to environment without manual configuration. So, this self configuration can refer to even in such cases where there is a failure of a node being detected. Even when a node fails, whether the other node can take up. How the other node can take up? They can take up provided they actually move around, if the nodes have got their own mobility, else they can also take up if they change maybe their slipping pattern. So, let us look at a simple mechanism to deal with this. So, we say that the nodes can be in active or passive state. Nodes which are in active state forward data packets, which using a routing mechanism that runs over the topology. Passive nodes do not forward any packets, but may sleep or collect network measurements. Fine. So, now each node joins network topology or sleeps according to measured number of neighbors and packet loss as measured locally. So, here this is an adaptation of a topology with no node movements, only making nodes active and inactive. So, I have got a set of nodes, and nodes are either in active or passive state, okay. And obviously, in this case what we can impose? We can impose greater sleeping period for the nodes. In a MAC it was fixed periods of listen and sleep. If I know a node is currently not participating in forwarding a packet, then the node can continue to sleep even if it has got now the time to listen, because it is not participating at all. So, each node checks whether you have got a certain neighbors in its neighborhood, that senses neighbors, as well as it senses whether there is a packet loss. If there is a packet loss, that means there may be a malfunction of a neighbor. So, to take care of that malfunction, it should activate itself. Okay. So, there is a therefore, an automated decision, an autonomous decision at the node level itself to decide whether to become active or passive. So, it is not just determined by the MAC protocol, but determined from the point of view of application, that is of packet transfer. The other interesting feature of these sensor networks at a higher level is data centric routing. Okay. So, typically you have seen routing is what? Routing means I route packets from source to destination, and there can be also intermediate nodes. Now, in a data centric routing, we say that we name data and not nodes with externally relevant attributes. Okay. We name data with externally relevant attributes. So, if the data is being transferred across the network, that means data is diffusing through the network, any node which needs the data can make use of these attributes and start using the data. So, this as a phenomena is different from that of a pure address centric routing, where the data is targeted for a node having a specific address. The address need not be an IP address, some form of address. So, what happens here is you diffuse requests and responses across network using application driven routing. So, this application driven routing can be geographically sensitive, can be trajectory based, because I might like to route the packets along the trajectory. The example of the tracking is typically a case when I have detected a particular target and I have got that information to the packet I am trying to send it along. You optimize the path, and these would support in network aggregation and processing, because if you have the data packet and moving along a track, and along the track if actually the target is moving, then at each node you can do what? You can aggregate the newly sensed data with already sensed data. So, that aggregation takes place in the network itself, and here when the data is being sent or being broadcasted, it is not really being sent to an address, but being broadcasted with a tag describing the data. So, the other nodes which are listening to it, they can really process that data depending on the request that is being diffused. So, what we say that the data sources publish data and data clients subscribe to data, and all nodes may play both the roles. Fine. So, a node that aggregates, combines, processes incoming sensor data becomes a source of new data. Okay. A sensor node that only publishes when a combination of conditions arise is a client for triggering event data, and it becomes a true peer-to-peer system. The implementation define namespace and simple matching rules with filters. What do we need matching rules with filters? Because I need to match the attribute of the data to know whether it is to be processed. So, it is not targeted for a particular node, but node understands whether it requires to process the data depending on the application request that it is processing. So, the basic model is that of publication of the data, that is publishing of the data, as well as consumption of the data depending on the demand. So, what we have in terms of comparison, because this data centric routing you will not find in a classical network. Classical network is always address centric routing. So, in an address centric routing, each path is from source to sink. So, you have got distinct paths from each source to sink. In a data centric routing, support aggregation in the network where paths or trees overlap. Okay, there may be multiple paths. So, that data centric processing can take place over such multiple paths, and this is the essential difference from traditional IP networking. So, this data centric routing, which is absolutely important for observing the phenomena in a sensor network, makes the whole routing exercise completely different from IP centric networks. Okay. So, these more or less finishes our basic characteristics of sensor networks. Now, we shall look at the issue of designing such a network based system. Okay. Designing of such a network based system, independent of what protocol being used, involves two aspects. One is communication analysis and system performance analysis. In fact, these aspects are important for designing either sensor networks, maybe a network of processors to go into SoC, maybe a network of embedded systems to put on a automobile. So, any such distributed embedded system design needs to do communication analysis as well as system performance analysis. So, let us try to understand them in a qualitative sense, not really in a analytical way. So, in a communication analysis, obviously the performance of networks depends upon delay incurred by transmitting messages, and delay for single message primarily is determined by the network transmission time, but delay for multiple messages depends on network protocols and devices on the network. Okay, because when you are looking at a single message, you can assume a reliable delivery of a single message, and you are not considering the multiple messages being delivered. So, multiple messages, whether they will be scheduled for delivering or not, also depends on the protocol being followed. It will also depend on the different paths the message is following. Okay. So, then the delay for multiple messages becomes difficult to analyze. Okay. And delay for single message is primarily determined by the network transmission time. Now, if we look at this, that a single message, reliable delivery and no contention, then the delay can be calculated by this formula. This is the transmitter time, this is the network transmit time and receiver overhead. And typically the network transmission time dominates the other two factors. So, for any design, if you have an estimate of these factors, that would enable you to take decisions. Okay. So, let us take a simple example of multiple, we shall look at an example with multiple processors when they are involved into in a network for a distributed computing task. On the other hand, if I consider multiple messages, the messages can interfere with each other and analysis becomes obviously more complex. So, we need to model the message delay. So, there are two aspects of it. One is your network availability of delay and the message delay. The message delay is what we had already seen. Network availability delay becomes critical when we are looking at multiple messages, because this is the availability of the network. What does the availability of network means? That the communication channel is being made available to the message for being transmitted. Now, so value of availability delay depends upon the type of arbitration used in the network, because arbitration will decide whether the communication channel will be available for transmitting a message or not. So, there can be various forms of arbitration. We have already seen when we have studied these buses as well as networks, there are various forms of arbitration which are used. If you use a fixed priority arbitration, then you get what is called an unbounded delay. If you have an unbounded delay, you cannot really design a real time system on such a network, okay, because you cannot guarantee the task being finished within a deadline. So, unless and higher priority devices are known to have limited rates that allow lower devices to transmit, you may have absolutely unbounded delay for the low priority devices. And delay, but obviously you can see that if I have a fixed priority, if I have a task with deadlines and if they are given the highest priority, then you can definitely satisfy those tasks. But with tasks with a lower priority can suffer from unbounded delay and their deadlines may not be met. Now, delay is bounded for fair arbitration. So, a very common fair arbitration policy is round robin. Okay. A round robin arbitration introduces bounded delay proportional to n. Why? Why should it be proportional to n? If there are n packets contending for the bandwidth, because it is given in turn, each packet or each source is provided with a slot in turn. Okay. So, obviously, the delay would be proportional to n, that is the number of packets contending for the slot. So, let us take an example, let us have a look at an example, and with respect to an example understand that what to do with these delays, okay, whether we can really redesign some aspects of the network to increase efficiency once we know these delays. The problem is indicated by this task graph. So, these are the tasks P1 and P2 and they produce data D1 and D2 which is required by P3 to complete the tasks. And you are using a network of processors to finish this job. So, there are 3 processors M1, M2 and M3. Okay. So, first we need a task mapping. Let us say we have done this task mapping. Once we have this task mapping, this task will take different times to get executed on these processing elements. And then they need to communicate these. Okay. So, I have shown the basic execution times, say 3 units, it does not matter what is the time unit, 3 units of time for P1 and P2 and 4 units for the transmission time. Now, if this is a setup, then what will be the total time required for completion of this task? So, I can draw this. So, I can have P1 and P2 scheduled concurrently because they are on different processing elements, but I cannot schedule P3 simply because P3 can only start provided it receives the data D1 and D2. And these data will take this amount of time. Okay. So, the total execution time in this case would be 15. Okay. Now, the question is, can I redesign the whole network based system to reduce the time? So, the question is to reduce time, P3 can be redesigned such that it does not require both the messages to start or maybe some part of the messages to start. So, it becomes the question of redesigning your task P3. This is basically your design problem. So, one way to do this is messages can be divided into smaller packets. So, the definition of a packet is a critical component here, and you modify P3 such that it reads one packet of D1 and one packet of D2 and computes partial result and continues to next packet. Okay. So, therefore, what it means that you can now schedule P3 overlap with actual transmission, because earlier P3 was getting scheduled only after transmission was complete. Okay. So, in this case I have divided the data into packets. So, these are D1, D2 correspond to packets of from task P1 or P2. So, once D1 and D2 is arrived, P3 can be scheduled. So, P3 now can be overlapped with the next packets from 1 and 2. So, these can continue, and so I can say that the P3 can finish in time say 12 units because it has been now overlapped with that of your packet transmission. So, this becomes an issue of design. This is an important aspect when we are looking at designing a network of processors on SoC, even when we are designing a set of sensor nodes to monitor a phenomenon. Because if you see all your collaborative data processing and signal processing tasks will have these kind of task dependence as well. Okay? And what is the data packet which are being broadcasted or transmitted, that has to be decided to have tasks performing in such a way that they meet the time constraint of the phenomena. There can be further complications because we have not taken into account acknowledgement time, transmission errors. So, that can be taken care of if you do a probabilistic analysis or a simulation. So, you can compute a probability that a packet will be delayed beyond an upper bound. So, that kind of an analysis makes this design process more sophisticated. There is also another important phenomena which happens in network based system is that of priority inversions. In many networks, a packet cannot be interrupted. In almost all the networks, a packet cannot be interrupted. A process can be interrupted, but a packet cannot be interrupted. So, what happens? A low priority message can hold up a high priority message. Okay, even if you have a higher priority, that cannot be sent since the low priority packet is currently in transmission. But these will not cause any kind of a deadlock because packets are of bounded length. So, packets will definitely get delivered. So, the next one will get a chance. But what happens is a priority inversion. Okay, we have seen priority inversion in the context of process scheduling. Here we are looking at priority inversion in the context of communication, packet scheduling. So, priority inversion would lead to what? Will slow down important communications. So, you need to know that how to deal with this slowing down. In fact, fair arbitration scheme also cannot prevent priority inversion because packet transmission cannot be interrupted. Okay. So, that may lead to design of separate networks, a network for a higher priority tasks, a network for, I should not say high priority task, high priority messages, a network may be for low priority messages. In case of a multi-hop network, one node receives message then retransmits to destination or an intermediate. So, in analyzing delays in multi-hop network obviously is much more difficult and needs to take into account the time taken at intermediate nodes. Because the intermediate node depending on the task would decide what to schedule and when to schedule. So, what we are therefore coming to the problem of communication scheduling. But scheduling of communication and computation is interrelated. Changing schedule of a process affects schedule of processes with which it communicates, because that process cannot start until and unless it gets the data from this process. And you may need to have to take care of the delay because of priority inversion, separate networks for high priority communication to minimize the effect of priority inversion. And the packet scheduling at router therefore becomes a critical component for delay sensitive traffic, because the delay that a packet would suffer depends on how the router decides to schedule. Which scheduling of a packet means what? Which packet being selected for transmission, that is allocation of communication channel. Okay. Now, related to this is the system performance analysis. Analyzing performance of distributed embedded systems is difficult in general because multiprocessors are involved and communication performance is also involved. Simple example here is uncertainty in P1 finish time implies uncertainty in P2 start time. Take an example here. I have got 3 processors and I have got independent tasks. P1 and P2 belongs to one task set, P3, P4 belongs to another task set. Now, P2 and P3 is mapped onto one processor. So, depending on scheduling of P2 and P3, P4 and P1 as well as performance of P1 would critically determine P2, because if P1 is delayed, P2 will be delayed. If P2 is delayed, P3 may not be scheduled. If P3 may not be scheduled, P4 may be delayed. So, P2 and P3 can delay each other even though they are in separate tasks. Okay. So, delays in P1 propagate to P2, then P3, then to P4. So, these kind of analysis becomes importantly to be done. So, scheduling policy of the processes themselves decides the scheduling policy of the tasks as well. So, if you look at the communication requirements, so this is a kind of bound you will get. So, this bound comes from say if TL is a LCM of the periods of the tasks, because many of these tasks are periodic tasks, LCM will give me the least common multiple of these periods. So, if Ti is a period of each task, then if I divide these, I get the number of times a task gets scheduled. I know this as a processing time of individual task. If I sum it up, that gives me the lower bound of the computational requirement. And a lower bound of the communication requirement comes from summation of this Li, because Li is a communication volume of process I over TL, because TL is a LCM of the period. So, that gives me the lower bound on the communication time. So, all analysis and design has to be based on these two parameters. So, when I am designing therefore, on the basis of these parameters, we need to choose processing elements and the types of networks, and we evaluate a platform by allocating process, scheduling processes and communication such that these requirements are satisfied. So, if you look at an IO intensive systems, which is typically maybe your sensor network, so you need to have the devices and sensors, identify the critical deadlines, allocate your processing resource accordingly, okay, and analyze your communication times, and then choose Ps to go with the devices. Okay. So, different Ps can go with different devices depending on your deadline. If you are doing a computation intensive tasks, you should start with the shortest deadline task, okay, and that should be put on different Ps. So, I am talking about a distributed system. So, they should be put on different Ps, and check for interference on critical communications, allocate lower priority tasks to common Ps wherever possible, and you need to balance loads. So, this is a typically a computation intensive system. So, this brings us to the end of our discussions on networked embedded system. So, we have studied today different aspects of sensor networks and looked at issues involved in designing of distributed embedded system. In the next class onwards, we shall basically look at these design issues in more detail.